Hello, welcome to this session. In this session, we are going to solve an interesting problem in radioactive process, and this problem is from one of the past JEE mains exams. Let us first take a look at the problem statement. An accident in a nuclear lab resulted in deposition of a certain amount of radioactive material of half-life period 18 days inside the lab. Tests revealed that the radiation was 64 times more than the permissible level required for the safe operation of the lab. What is the minimum number of days after which the lab can be considered safe for use? Okay, so let us take a look at what is given and what we are required to find. So there is an accident in a nuclear lab and that resulted in deposition of a certain amount of radioactive material. So it is not specified how much of radioactive material, just a certain amount. The quantity is not specified here. And this radioactive material has a half-life period of 18 days. And right after the accident, the radiation level is measured and it is found to be 64 times more than the permissible level. So there is a certain level of radiation that is considered safe, that is considered as the permissible level. Now right after the accident, the radiation level has spiked to 64 times more than the permissible level. And we are required to find after the minimum number of days after which the lab can be considered safe for use. So what does it mean that the lab can be considered safe for use? It means the radiation level is same as the permissible level. That is, we need to find the minimum number of days after which the radiation level reaches the permissible level. Okay, so this is what we need to find, reaches the permissible level. That's when the lab can be considered safe for use. Okay, so now we have understood what is given and what we are required to find. Now let's talk about how we are going to solve this problem. Okay, so first thing is we need to find the relationship between the radiation level and the number of days passed. Then only we can determine after how many days the radiation level reaches the safe level, that is the permissible level. Okay, so this is what we need in order to solve the problem. If we know the relationship between the radiation level and the number of days passed, then we can find the radiation level at which, the number of days after which the radiation level reaches the permissible level, and that solves the problem. So first let us talk about this radioactive process and the source of radiation. Okay, so let us say there is a certain amount of radioactive material deposited, right? The quantity is not given. Let us say there are like 10,000 nuclei, just an example. Okay, now what does this mean, this half-life period of 18 days? So after 18 days, okay, what happens during this 18 days period, half of this nuclei, that is 5,000 nuclei, will decay, okay, over this period of 18 days, and 5,000 will remain. And then over the period of next 18 days, half of this nuclei, that is 2500 nuclei, will undergo decay and remaining will be 2500, and this process continues. Okay, now this is how the radioactive process continues. Okay, and here this decaying, right, 5000 nuclei decaying, here 2500 nuclei decaying. So these are the source of radiation. Okay, these are the source of radiation. Now the first thing that we need to understand is the radiation level, right? This radiation level, let me write it here. The radiation level is directly proportional to the decay rate. Let me explain what is this decay rate. So here you see, in this period of 18 days, 5000 nuclei are decaying. So that means 5000 decays over a period of 18 days. This is the decay rate. Here you can see 2500 decays over 18 days, the same period of 18 days, and here it will be 1250 decays over the period of next 18 days. So here this radiation, this decay rate will be 1250 decays over 18 days. So this is the decay rate, that is the number of decays over a given period of time. Now this is actually the average decay rate over this 18-day period. This is the average decay rate over this 18-day period, 18 days period. Okay, so here the radiation level at a given instant, at a given time, is directly proportional to the decay rate at that instant. Okay, the instantaneous decay rate, right? So because these decays are the source of radiation, and that's why the radiation level is directly proportional to the rate at which the decays happen. So this is the first thing we need to understand. And the second thing is the law of radioactive decay. This states that this decay rate, right, the decay rate is directly proportional to the number of nuclei, okay, at a given time. It's directly proportional to the number of nuclei present at that instant of time. Okay, what does this mean? The rate at which the nuclei decays, right, the number of decays per time with time. So that itself is dependent on the number of nuclei present at that instant. So let's take this example. Here we have 10,000 nuclei, okay, and during this 18 days 5,000 nuclei decay. But here in this 18 days, not 5,000, only 2,500 decays occur, and here in this 18 days just 1,250 decays occur. So you see the decay rate itself is decreasing, right? And you can also see the number of nuclei is decreasing, right? So this is what explained by the law of radioactive decay. Actually here in this example I am talking about the average decay rate, but here it's about the instantaneous decay rate. So the decay rate at a given instant is directly proportional to the number of nuclei present at that instant. So this illustration can help you understand this law. Okay, even though we talk about the average decay rate, it gives an idea of how this radioactive decay law works. Okay, so now if you combine these two, that is the radiation level is directly proportional to the decay rate at that instant, and this decay rate at that instant is directly proportional to the number of nuclei present at that instant. So that means this radiation level is directly proportional to the number of nuclei present at that instant, right? So that is radiation level is directly proportional to decay rate here, and this is proportional to the number of nuclei, okay, at a given instant of time. Radiation level is directly proportional to the decay rate, which in turn is directly proportional to the number of nuclei present. Okay, so that means radiation level is directly proportional to the number of nuclei present. Okay, and this number of nuclei reduces with time, decreases with time. Okay, that is given by the radioactive decay equation. The number of nuclei present at a given time is equal to the number of nuclei present at time t equal to 0 into e power minus lambda t, right? And this lambda is the decay constant. So this is the equation that gives the number of nuclei at a given instant of time. Okay, so we know that this number of nuclei present decreases with time. Okay, and the radiation level is directly proportional to the number of nuclei present. So that means we have this link, the link between radiation level and the time passed. That is, radiation level depends on the number of nuclei present, and which in turn depends on time. So that means radiation level decreases with time, right? This is the link that we were looking for. Now with this understanding, let us write the mathematical statement for this problem. Okay, let us say let r of t be the function which gives the radiation level at a given time. Okay, time t. Okay, and n of t is the number of nuclei at time t, and we have established that this r of t is directly proportional to n of t. Okay, and in the problem it is given r of 0, radiation at time t equal to 0, is 64 times the permissible level. Okay, 64 times permissible level. Let's say let L be the radiation level which is considered permissible. Okay, L is the permissible level of radiation. So radiation at time t equal to 0 is 64 times L. This is given in the problem. And let us say after a time period of t, okay, the radiation level reaches the permissible level, that is radiation at time t is L, and we need to find t. Okay, this is actually the problem. So we need to find the number of days after which the radiation level reaches the safe level, permissible level. Okay, that means r of t equal to L, and we need to find t. So for what value of t, r of t will be L. This is what we are required to find. Okay, so now this constitutes the mathematical formulation of the problem. We have n of t and we have r of t, which is still not yet defined. We don't have the equation actually, but we know r of t is directly proportional to n of t, and in the problem it is given r of 0 equal to 64L, and we are required to find this t such that r of t capital T equal to L. Okay, so now let's make use of this proportionality. What does this mean? R of t directly proportional to n of t, and we know r of 0 equal to 64L. So r of 0 by, since they are proportional, n of 0 equal to r of t by n of t, right? Directly proportional, right? So at time t equal to 0, the ratio of the radiation to the number of nuclei is equal to, at time t capital T, the radiation level, the ratio of the radiation level to the number of nuclei. Okay, so now this is equal to r of, sorry, here you can write r of 0 is 64L divided by n of 0 equal to r of t is L, right, divided by what is n of t, 0 into e power minus lambda t. Okay, and this lambda is the decay constant. We will come to that shortly. Now you can see this gets cancelled, L gets cancelled, so all that remains is e. This we can move to the numerator, e power lambda t equal to 64, and taking natural logarithm on both the sides, we get lambda t equal to ln 64. Now what about this lambda? The relation, actually in the problem they have not provided anything about the decay constant, but they have provided the half-life period. So the relationship between this half-life period and the decay constant is given by lambda t half-life. This, let's write t half as the symbol for half-life period. This is equal to ln 2. Okay, this is the relationship between decay constant and half-life period. So let's make use of this here. So that means instead of lambda we can write ln 2 divided by half-life period into t. This t is what we need to find. Okay, equal to ln 64. Now itself you can see we have almost solved the problem. Now t equal to, what about ln 64? The 64 equal to, in terms of powers of 2, 2 into 2, 4, 8, 16, 32, 64, 1, 2, 3, 4, 5, 6. So this is equal to ln 2 power 6. That means t equal to 6 ln 2 and this ln 2 will come here, it gets cancelled, and T half. Okay, now T equal to 6 times the half-life period, that is 6 into what is the half-life period, 18 days it's given in the problem, right? So that means 6 10s are 60, 6 8s are 48, so totally 108 days. This is the answer. So after a time of 108 days, right after this time duration, the radiation level reaches L. The radiation level reaches L, that is 108 days. Okay, so that solves the problem. Now let me mention one more thing here. Actually there is another way also to do this problem, just using this fact that radiation is proportional to the number of nuclei. So here you can see, let's replace this 10,000 by n. There are n number of nuclei. We don't know the quantity, right? They have just mentioned a certain amount of radioactive material, and here it will be n by 2. Okay, here it will be n by 4, and so on. Now let's say here the radiation level is 64 L, right? That's given in the problem. So that means using the proportionality level, here we don't know the radiation, let's say R. Okay, so that means n by 64 L equal to n by 2 divided by R. This implies R equal to n gets cancelled, 64 L by 2, this is 32 L. So radiation level here is 32 L, that is half of this radiation level, because the number of nuclei has halved here. The number of nuclei has come down by half of this value here, and likewise the radiation level has also come down by half of this value. Okay, and if you continue the process likewise, you can see, so here I can write n by 2 divided by 32L equal to n by 4 divided by the radiation level, let's say R here. So that means R equal to n gets cancelled, 32L by 4 into 2 to 16. So that means 16L. R equal to 16L. So here it will be 16L. And you can continue this calculation, and eventually you will see, so 18 days, 18 days, 18 days. So 6 times 18 days. After that you will see this 16 level becomes 8L, and then 4L, and then 2L, and then it will be L. So after 6 times of 18 days you will see this calculation reaches L. So that is also another way, but this is a better way because this doesn't depend on this initial level. Suppose instead of 64L, if it's a very high value, means that it will be very tedious process to continue this iteration. So this is a much better approach, but I just want to highlight, you can just see the relationship between the number of nuclei and the radiation level. Okay, now with this I think we can conclude this session, and I hope this session helped you in your learning. So we will meet again in another session. Thank you.